Good day, statisticians. Here today, we're going to learn to do a one-sample t-test for a population mean. And you might wonder, well, we've already done tests about a population mean. Why do we need to learn something new, a t-test? Well, as you recall, when we were doing confidence intervals, we learned that if you know sigma, which is the population standard deviation, then we can use all the things that we know and use a normal curve for our confidence intervals and for our significance tests. And when we use a normal curve, we write our test statistic and our critical values in terms of z, because that's related to a normal. But we'll see when we're doing a t-test, we'll be in a much more realistic scenario where you have an unknown sigma, right? You don't know the population standard deviation. Instead, what do you know? You just know, only thing you know is the sample standard deviation, S. And of course, you can always know the sample standard deviation because you'll have a sample of data and you'll just calculate the standard deviation and then you've got it, right? The population standard deviation, why the heck would you know that? Most of the time, it doesn't make any sense at all that you would know the population standard deviation if you don't know the population mean, mu. Like, what makes you think you would know sigma if you didn't know mu? There are maybe some scenarios where that would be the case, but for the most part, that seems pretty unrealistic. And so in general, when we do anything that involves a population mean, whether it's a confidence interval or significance test, we'll almost always, 99.9% of the time, just go ahead and do a t-test, right? And that's because we can always know a sample standard deviation, but we'll very rarely know the population standard deviation. So let's see an example that takes us through the whole process. So here we go. Here we've got a scenario where we're looking at a classic rock radio station claims to play on average 50 minutes of music every hour. 50 minutes of music every hour. The other 10 minutes is like commercials and maybe talking and stuff. But however, it seems that every time you turn to this station, there's a commercial playing. Needless to say, you think it is less than 50 minutes, the amount of time you get music. To investigate their claim, you randomly select 12 different hours during the next 2 weeks and observe the total time played in each of the 12 hours in minutes. And so the key idea here is they make this claim that on average you get 50 minutes of music, right? And so if we start to set up our test, our null hypothesis will be that mu equals 50 minutes. And the alternative hypothesis will be that mu is what? We kind of think it is less than 50 minutes, so we'll do less than 50 minutes. Let's make sure we define our parameter, that mu equals the true average say duration of music on the hour of music per hour by the radio station. All right, that says radio station. Okay, so that's stating our main stuff. We're going to do a significance test. We might as well say what level of significance we're going to use here. I'm not going to really worry too much about a type 1 or a type 2 error. Let's just make our alpha something basic like 0.05. Okay. So in this procedure, we're doing a test about a mean, right? And do you see the population standard deviation given here? What's the average difference between each hour's amount of music and the true average? No, that's not given us anywhere. All we have is this data from the 12 hours that this person actually collected music. And so the only standard deviation we're going to be able to deal with is the standard deviation of these values. That's why we're going to have to do a t-test rather than some other kind of test like a z-test. So, all right, let's check the conditions for a one sample t-test for mu, right? Okay, now for this one sample t-test, we'll begin just like we always do and check for randomness and independence and stuff like this. Randomness, right? And the idea here is that these were randomly selected hours, right? Over 2 weeks. I think it says over the next 2 weeks. I just underlined 2 weeks there. So it's randomly selected hours, so that's a good thing, right? We'll say a couple things about independence. Independence. That says independence. Sorry, I'm writing quickly. Independence. We'll say, first we'll assume the amount of music from 1 hour to the next, from 1 hour to the next is independent, right? So we'll always assume that however much music they play during 1 hour is going to be independent of the amount of music they play another hour. So that's nice. But we'll also check the 10% condition in relationship to independence because we're going to have to assume that our random selection of 12 hours, so that we actually know how many hours are there in 2 weeks, right? What's the population of the total number of hours? Well, there's 24 hours a day times 14 days in 2 weeks. That's 336 hours. So we know capital N equals 336 hours, right, is greater than 10 times 12, which equals 120 hours, right? So we meet the 10% condition. Now, the last thing we'd have to check here is the special condition that's just for a one sample t-test from you. These other things, randomness, independence, is for every single time we do any inference procedure. For a one sample t-test from you, we're going to end up going to this. And this is actually a lot like, not technically, it's not the central limit theorem, but it's just like the central limit theorem. And we saw this when we did confidence intervals, right? If we know the population is normally distributed, we don't have to worry about any special conditions. We can go ahead and use the t-test. However, if the shape of the population is unknown or it's known to be non-normal in some way, we need n to be at least 30, right? And then, of course, there is one other scenario. What if n is less than 30? Then we're going to check our sample and make sure we don't see any real significant skewness or outliers that might mess up our ability to go ahead and assume that the population is close enough to normal to use the t-test. So that's what we'll have to do. I'll have to check. So when I look here, I see my sample size is, oh no, so sad. My sample size is only n equals 12. That's less than 30. So that means I can't just say that my sample is large. I'm going to have to check my sample for skewness and outliers, right? And so maybe I'll go to the next page. Let me get another blank piece of paper, and I'll check this last condition where I have a little bit more space, right? So let's say here, to check the large sample condition, right, I would say here too, the large sample condition, not large counts, but large sample. I'll say since my sample size is less than 30, I need to check the sample distribution, not the sampling distribution, but the samples distribution for skewness and outliers. And so this, unfortunately, I'll have to do by taking all the data and sticking it in my calculator. I'm checking this for skewness and outliers. Now, luckily, I was thinking ahead. I did this earlier. See how I got all the numbers in there? But we're going to go type in 44, 49, 45, blah, 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 blah. Type them all in, and then I'll hit second y equals. I'll make sure my first plot is on. I'll make a histogram for L1. That's where I had all my data. And then I'll hit zoom option 9 and I'll get a little histogram. And that's a funky looking little histogram. But I'm going to draw a quick sketch of it. And this doesn't have to be perfect. Sometimes what I actually do is if the screen is bright enough, I can sort of stick the calculator underneath and see. Right now it's not quite working for me. So let me just draw a quick sketch. There we go. That seems to be kind of taller. That's a little bit less. This is a little bit less. This guy's the tallest. Ooh, should really be about equal width. And then these guys are the same. So when I look at this is the sample distribution. This is the sample distribution, right? And I'll say that I see no significant skewness or outliers, right? And therefore I can use the TProcedures, whatever the heck they are. In this case, procedures. I'll write out the word, right? TProcedures, because that works. All right, so that was all the most annoying part. Remember that checking the conditions is always really the most annoying part of the procedure. I had to do two things. I checked for randomness and independence, and then I checked the large sample condition because we wanted to do a t-test. All right, so now what do we have left? Well, just like always, we stated, we planned, now we've got to do. So we'll need a minimum, a test statistic, and a p-value. When we're doing a one sample t-test, then essentially, let me get the blue marker here. The test statistic, instead of being a z, will be a t, but it'll still be just a formula like a standard score, or like a z-score. So To get this, we'll take our sample mean, we'll subtract from it the hypothesized mean based on our null hypothesis, and divide it by the sample standard deviation divided by root n, right? Which is the standard error of the mean, right? Now, we're not using the true standard deviation, but it's the standard error formula because it's based on a sample statistic, right? And so let's go. What was our null hypothesis? The null hypothesis was 50, right? Now, what was the sample mean? Well, the only way I could know is if I hit stat, calc, 1var stats. Let me see here. The sample mean came out to 47.83 repeating. So I'll do 47.83 approximately. And let's see, my sample standard deviation was 2.6571. 2.6571 divided by the square root of 12, right? And so if I put this in my calculator, I could do 47.83, remember there's a bunch of threes, minus 50, right? And then I'll divide that by 2.6571 divided by the square root of 12. And let me close parentheses, and I got a test statistic of, so you're negative 2.8247 approximately, right? And so that is my test statistic. All right, let me make that in red so you can see it. Boom, that's my test statistic. Now to get my p-value, instead of using normal CDF, right? Remember, the real deal here is I want to figure out what's the probability of getting a sample mean that was less than 47.83 repeating, given that that mu is actually 50, right? That was the probability I was trying to calculate. Well, that'll just end up being the same thing as the probability that z is less than negative 2.8247. And now, I said z, stupid. It's t because I'm working with the t-distribution. Now, since I'm working with the t-distribution, I can't use normal CDF. I will use, what will we use? TCDF, right here, option number 6 in my calculator. A lot of you guys will have it be option number 5 because you don't have inverse T, so sorry, you've got an older calculator. But for me, option 6, TCDF, and I'll put as my lower bound. What's my lower bound here? Well, it's, again, I want something less than something, so do like negative infinity. The upper bound would be my test statistic, 2.8247, right? And then, the DF, the degree of freedom. Right? Just like power and degree of freedom. We got all these crazy words. So what's the degree of freedom for a t-test like this? Well, remember, actually, this degree of freedom is going to work out just the way we like from before. The degree of freedom for a t-test is going to always be n minus 1, right? And that's not for all t-tests, but for a one sample t-test, that's going to be our degree of freedom. We're going to see next week where we're going to have degree of freedoms that are calculated in a pretty crazy way, man, right? But for us, for right now, that's easy. Our sample size is 12, so therefore our degree of freedom is 11, and I'm going to put that in my calculator. Now, interestingly enough, I'm going to add a third thing to our list. When we're doing a t-test, you should say what the test statistic was, what the p-value was, but you should mention the degree of freedom, right? What was the degree of freedom for what you use to calculate your p-value and as you're showing your work? Because if you use the wrong degree of freedom, things aren't going to work out. So I'm going to write my degree of freedom as 11, and then I'll hit paste and Shazam. There I've got, wait a second here. What did I do wrong? Oh, I just noticed, I forgot to put the negative in for my t. So maybe you noticed that before, I missed it. So I'm going to go back here. I'm going to make that insert a negative and hit paste, and bam. I have a p-value of 0.00826. So my p-value is 0.00826. And let me make that bolder. And so there we go, right? With this kind of result, what does this mean for us, right? Well, I'm going to try to fit in my conclusion here I'll write down my conclusion down here at the bottom, right? What will we do? I'll say since the p-value, which equals 0.00826, is less than alpha equals 0.05, I reject the null hypothesis, right? Therefore, I do have significant evidence that what? Well, I'm rejecting the null hypothesis. That means I have significant evidence in favor of the alternative. That means that the true average duration of music on the hour, music per hour at the station, whatever radio station this one is less than 50 minutes. Just barely managed to squeeze that in, right? But I do have significant evidence that the amount of music played per hour at this radio station is less than 50 minutes because I rejected the null hypothesis. Cool, right? All right, now, I want to take a step back. I did this whole, let's go back to the do real quick. Remember the do, I calculated that entirely by hand. We could have done that as a shortcut in the calculator. Let's go over to our tests. And which one do you think would have been the correct shortcut here? How about t-test? Oh yeah, let's t-test it, right? Fun fact, because I already did one var stats, it already pasted in the mean and the sample mean and the sample standard deviation based on stuff, right? I do have to change what the null hypothesis is. What was my null hypothesis? I can make it 50, right? And then I've got the mean, I've got the standard deviation, I've got 12, and this was a less than test. Let me hit calculate and boom. Notice right there, it has the exact t-test statistic and the p-value, and it didn't require me doing and showing all this work and using TCDF and all that stuff. And so this is just as good when you're doing the test. The screen won't tell you the degree of freedom, but you should mark down what degree of freedom was the correct degree of freedom used in this case. We'll see that when we start doing 2 sample t-tests next week, that's when we'll actually have perhaps some potential disparities in the degrees of freedom we'll choose, and therefore it's really important that you say what it is. So for a t-test, make sure you mention the degree of freedom. Okay, guys? Now, just fun fact, we just mentioned that we had evidence. I'm going to do one more thing. We had evidence that we should reject the null hypothesis. The amount of music per hour is less than 50 minutes. If I really wanted to know how much less, then I should make a t-interval, right? And we learned to do this before. If I just made a t-interval with that sample mean and that sample standard deviation, and I picked the confidence level, and since I did 5% significance, remember that would kind of correspond with a 90% interval, but you could pick whatever percent interval you want to do. But let me hit calculate, and with 90% confidence, I could estimate that the actual amount of music per hour at this radio station is somewhere between almost 46 and a half minutes to 49.2 minutes. So my estimate suggests that it is definitely less than 50 because 50 is not in this interval. But notice this is only a 90% confidence interval, only 90% confident that this would capture the truth. But it does tell me more information than simply saying reject the null hypothesis at 5% significance, right? Anyway, guys, is that helpful? I hope it is. I hope you have a beautiful day and you'll be okay doing the same kind of process with different sets of data. Remember, the only extra special annoying thing we had to do is actually make, this is a really terrible histogram, but this would be sufficient. But you have to make a histogram to show that the large sample condition is satisfied whenever your sample size is less than 30. Thank you guys. Have a beautiful day, and I'll catch you on the flip side.